Right, so this is the video for exercise 7C, solving problems using nth terms of a geometric series. So in this question we've got Andy invests £8 at a rate of interest of 4% per annum, so that's 4% per year. So this is actually going to involve a topic from GCSE called multipliers, to try to think and remember and remind yourself of what that is. So after 5 years it's going to be worth 10,000. How much, the nearest penny, will it be worth after 10 years? So first of all, we want to look at what the common ratio is. All right. So like I said, the common ratio is going to be a multiplier. Okay. Now if it's a rate of interest, it's going to be a percentage increase question. So 100% plus 4% gives us 104%. Then if you remember, the multiplier then comes from converting that percentage into a decimal. If it was going to be a percentage decrease question, you'd take away that percentage from 100 and then convert it to a decimal. Okay, so before we jump straight into this, I just want to look at how the pattern would build up. Okay, you'll see why now. So after 1 year, Andy would have had his investment for £8 in the bank, and then that would be increased by 4%. So after 1 year, he'd have A multiplied by 1.04 in his bank account. So after 2 years, he'd have the A multiplied by 1.04 that he has in the bank after the first year. Then that would be increased by 1.04 as well. So after 2 years, he's going to have A times 1.04 times 1.04. As the video goes on, you might have an idea of what the nth term is going to be. It's going to be slightly different to what we were doing in exercise 7C, so beware. So after 3 years, you'll have the A multiplied by 1.04 multiplied by 1.04 from after 2 years, and then multiplied by a further 1.04. Okay? So if you look at the number of years and the number of times that multiplier is used, we can say the nth term is going to be A multiplied by 1.04 to the power n this time. So when the question is in a real life context, you want to just go through that process I've just done just to make sure that you've got the nth term correct, because it's the nth term in 7C was AR to the n minus 1, so you don't want to just dive straight into that. You'll be careful of the way the question is worded. So we've got to find a value of A. If you plug all that into our nth term, we've got A times 1.04 to the power 5 is equal to 10,000, because we've told after 5 years it's worth 10,000. So if we solve that equation, we can work out what Andy's initial investment was. So just move that up to there. So if you stick that into a calculator, 10,000 divided by 1.04 to the power 5, then that's going to be 8,219.271068. And we could round that to 2 decimal places, so we know that he's invested £8,219.27. Just a bizarre amount to decide to invest. But that's not the answer we've been asked for, though, so I want to keep that answer unrounded. We're only going to round the final answer, which is what's going to happen now. So if we put that A equals 8,219 and n equals 10 back into our nth term, we'll be able to work out the 10th term, which would be the investment after 10 years, which is the calculation I've just written out. Okay, and that's going to give us 12,166.52902, and it's that number that we're going to round, because that is our answer that the question has asked us to calculate. It's asked us to calculate how much to the nearest penny will it be worth after 10 years. So we're going to finish our work off with a little conclusion, right? A little statement, a sentence just rounding up what we've done. So we just want to say, therefore, after 10 years, Andy's investment is going to be worth, so after 10 years, the investment is worth £12,166.53. Okay? Done. Let's do another example. Okay, so our next example, we want to find out what's the first term, the geometric progression. It's just another word for a geometric sequence. 3, 6, 12, 24, to exceed 1 million. So that word, that phrase, to exceed, is going to lead us to possibly thinking about using an inequality maybe. So let's get our values then. So we know this is a geometric sequence, so we can use our nth term for a geometric sequence. A is 3, common ratio is 2. So we know our nth term is going to be 3 multiplied by 2 to the power n minus 1. Okay? So what's the first term to exceed 1 million? So that means we want to find a term, so an nth term, whose value is bigger than 1 million. It's the first one. So therefore, we want to find out when the nth term exceeds, so is greater than 1 million. Okay? So therefore, we're going to work out when 3 times 2 to the power n minus 1 is greater than 1 million. So now that might cast your mind back to a recent topic you've looked at, as we've got the n that we are trying to work out is in the power. So the method we've looked at recently to solve equations like that has involved logarithms. Alright? So let's start solving this then. So if we take the 3 across first, so we can have 2 to the power n minus 1 is greater than 1 million divided by 3. And because that will give us an awkward decimal number, let's just leave that as a fraction. Alright? And I'll calculate it to the work for us later. So to bring that n minus 1 out of the power, so that we can solve it, what we did in the logs chapter is we took logs of both sides, so log to the base 10 of 2 to the power n minus 1, and logged to the base 10 of 1 million divided by 3. Okay? And the reason we do that is so that we can bring that power out of the log. Remember, using the power rule. So that was this rule in the logs chapter. If you've got log of a to the power b, we can bring that b out, so it's b log a. Okay? If you're a bit rusty on the work we did on logs, maybe an idea to pause the video and go to my maths and do a little bit of revision on that maybe. So that's going to give us n minus 1 times log to the base 10 of 2 is greater than log of 1 million divided by 3. I'm just going to call it log to avoid having to say log to the base of 10 all the time because I'm getting tongue-tied. Right, now this next bit is a little bit awkward, okay? We need to take that log 2 to the other side, so we get n minus 1 on its own. Alright, so that's going to be n subtract 1 is greater than log of 1 million divided by 3 divided by log of 2. Now, if you remember in C1, our work on inequalities, that you've got to be careful with when you're solving an inequality. Because if you divide both sides or multiply both sides by a negative number, that means the inequality sign needs to be flipped. Now, when you look at log 2, you can't. It's hard to decide whether that is a positive or a negative. So on your calculator, just do a little check. When you're doing this kind of algebra, just work out that log. So log of 2 is 0.301, so we know it's positive. So when we take it across, we divide by log 2, because we're dividing by a positive number, we don't have to change that sign around. Okay? If it was negative, we'd have to flip that sign around. But obviously, in this case, we don't have to because it's a positive number. But don't just assume it's going to be a positive number. Always check. Okay? There are some questions in the exercise where the thing that you're going to divide by is a negative number, and you wouldn't spot that it's a negative number unless you work that out on your calculator. Okay, so just be a bit wary. Now, as you can see, we've run out of room on this slide, so we're just going to go onto a new screen and carry on working on this example, okay? We're just going to take that across to the next screen. Okay, so this is what we came to. n subtract 1 is greater than that horrific looking fraction. So we just take the negative 1 across to the side. That's going to give us log of 1 million divided by 3 all divided by log of 2, add 1. Okay? Now, if you've all got those calculators that do the surds and the radians in pi and all that cool stuff like I've got, all you need to do at this point is type that into your calculator so it looks the same in the display. So your calculator's got a thing called textbook display, which means you can write it as it is in your textbook into the calculator. So if you just take your time doing that, hit the equals button, you'll get n is greater than 19.346. So the next number that's greater than 19.346 is 20, and that's our answer. So, what's happened there? Let's shrink all this and put it up to there. Okay? So we can just check that. Because obviously that n is going to have to be a whole number because it's in a position in the sequence, isn't it? So we know through that work with the inequality that the first term in the geometric progression to exceed a million would be the 20th term. Okay? And if you just want to double check that to make sure that works, you just substitute. So there's our nth term again, look. Just copied that over from the previous slide. If you just substitute 19 and 20 into the nth term, so you work out the 20th term, using that, which is going to be this big number here I'm writing down, 1,572,864. Work out the 19th term as well, the same way. So you're just going to change that power 19 to 18. And if you work that out, so yeah, I'm changing that 19 to, that 19 will become an 18. If you work that out, you've got 786,432. Okay? So there you go. Double checked it as well. There's our answer. The 20th term is the first term, that geometric progression to exceed a million. All right. You ready now then to have a go at exercise 7C? Good luck.